Welcome back to The Deep Dive, the place where we cut through the noise and give you the essential knowledge on the most groundbreaking work happening in AI and optimization.
It's great to be here.
Today, we are undertaking a monumental deep dive into an algorithm that might just fundamentally change how we train the largest, most complex neural networks in existence.
It's a big one.
We're talking about EGGROLL, evolution-guided general optimization via low-rank learning.
Yeah, it's just this stunning piece of work, right? It marries, deep theoretical analysis with some really brilliant engineering. For decades, the field of machine learning has been, obsessed with gradient descent and backpropagation.
It's been the only game in town, really.
And EGGROLL really challenges that hegemony. It does it by solving the single biggest problem that's been plaguing these alternative methods for years: scaling. It allows evolution strategies, or ES, to finally handle modern hyperscale models.
And we're not just talking millions of parameters.
No, we're talking billions.
Exactly. And, evolution strategies aren't new. They're a classic concept, but they've always been sort of perpetually constrained by these practical bottlenecks.
Always.
So before we dissect how EGGROLL cracked the scaling code, let's quickly establish the basics for anyone who's been living firmly in that gradient descent world. What exactly is an evolution strategy, and why do researchers find it such an attractive, sometimes even necessary, alternative to calculating derivatives?
Right. So at their core, evolution strategies are a family of really powerful black box optimization methods. Think of it like this. Standard optimization, like you said, it requires calculus.
You need the gradient.
You need the gradient. You calculate it. It's essentially the mathematical slope, and it tells you the exact direction you need to step to climb the hill's steepest. ES doesn't do that at all. It takes a population-based, much more exploratory approach.
So instead of one precise calculation, it's more like sending out a search party.
That's a great way to put it. Instead of a precise calculation, ES generates an entire population of candidates. It does this by introducing small, random perturbations, or, noise, to the core set of parameters.
Okay.
Then it evaluates the fitness or the performance of every single one of those perturbed members. Only after it sees the results, the outcome, does it aggregate those results and move the core parameters in the average direction of the members that performed best.
So it's optimization guided by observation and outcome, not by some derived internal calculus.
Exactly. And when you describe it that way, you can immediately see why it's so useful, especially as our AI systems get more and more complex and integrated with the real world.
I see three core advantages of this ES approach that really set it apart and position it as a potential game changer. The first, and maybe the most foundational one, is non-differentiability.
That's absolutely the starting point. ES can optimize systems where the standard tools of calculus they fail. If a function is discrete, or if the objective itself is just an outcome-only reward, you can't calculate a derivative.
Can you give us an example of that?
Sure. Imagine a model that has to make a single decision, like whether to use a specific external tool or a memory module, and it only gets a reward signal, say, hours later. Backpropagation needs a continuous, smooth path to trace that reward all the way back to the initial parameters.
Right, a differentiable path.
Precisely. And with ES, if the gradient is 0, or if it's super noisy or just completely unavailable, like with models that have discrete parameters, maybe some form of sparse quantization, or when fine-tuning a large language model based purely on a scalar reward like win-loss in a game ES, just doesn't care.
It doesn't need that path.
It doesn't. It just looks at the output result, the fitness score, and adjusts the population accordingly. It completely frees you from the constraint of needing these smooth, continuous functions to optimize.
The second advantage is one of robust training, which feels more and more relevant as these models grow to just astronomical sizes. We know that optimizing these massive neural network landscapes is incredibly challenging. They can be ill-conditioned, filled with discontinuities, or suffer from all these chronic gradient issues.
Correct. That population-based exploration, it acts as an inherent smoothing mechanism. When you're surveying the landscape using, say, 1,000 different points all at once, you're getting a broad statistical understanding of the environment.
You're not just relying on a single data point.
Right. You're not relying on a single, potentially noisy or misleading gradient calculation from one spot. This makes ES inherently more robust to those local minima, to discontinuities, and crucially, to problems like vanishing or exploding gradients that just plague deep, recurrent, or long-sequence gradient training methods.
Which means it helps avoid all that instability that forces researchers to add, normalization layers or these complex gradient clipping techniques in standard training pipelines.
Precisely. You are inherently mitigating that instability just through distributed exploration.
And the third advantage, which I think ties directly into why EGGROLL even needs to exist, is this incredible potential for massive parallelization.
This is absolutely critical in the era of large clusters and TPUs and GPUs. Think about standard distributed gradient training. You have to communicate and aggregate these absolutely massive gradient tensors across potentially hundreds or thousands of GPUs.
It's a huge communication burden.
It's a massive memory bandwidth and communication burden that very quickly becomes the bottleneck. With ES, it's totally different. Every worker, every member of your population performs its fitness evaluation entirely independently.
They don't need to talk to each other during that forward path.
Not at all. All they need to communicate back to the central optimizer is a single number, their scalar fitness value. This minimal communication requirement, we're talking just a few bytes per worker, maps beautifully, almost perfectly onto modern infrastructure. It promises theoretical near-linear speedups on massive clusters.
Okay, so it sounds like an optimization utopia. Yeah. You've got low communication overhead, high robustness, the ability to train systems where calculus doesn't even apply.
Yeah.
And yet, for all these theoretical upsides, ES has been, a pretty niche player. It hasn't been the primary tool for training GPT-4-sized models.
Not at all.
Okay, so let's unpack this. If the concept is so scalable in theory, what stops standard ES from actually handling models with billions of parameters?
Yeah.
Where is the practical obstacle that EOLs had to solve?
The obstacle is surprisingly simple in concept, but just brutal in practice. It's a computational bottleneck related to generating the perturbations themselves.
Okay.
The whole deep learning paradigm relies on these massive weight matrices, which we can call dollars, right? When you run a naive or a standard ES, you have to generate and then evaluate a full rank matrix perturbation. We typically call this a GWAL, where dollars is a matrix and 1 AROL.
Right, and just for our listeners, if a dollars and dollar are the dimensions of the weight matrix, say something like 10,000 by 50,000, that's a 500 million parameter layer right there. And full rank means that the perturbation, the alarm matrix, has to have as many degrees of freedom as the original weight matrix itself.
Exactly. Now, amplify that across an entire billion parameter model. And then if you want a population size, we'll call it nuller, of, say, 10,000 workers, to get a really robust search signal.
Which you need.
Which you absolutely need. You now have to generate, store, and move 10,000 separate copies of the billion parameter perturbation dolls in memory. This just dramatically inflates your memory costs and forces the constant movement of these immense weight tensors all over the network and GPU memory.
So the memory and compute just scales prohibitively. You literally have no dollar copies of the full model's perturbation. This must be why all that previous successful ES work, even when it demonstrated capability, was so severely limited. I think I saw a number like a maximum population of 1,440 members.
That's the ceiling. That's the ceiling that the brute force approach imposes. The compute time and the wall clock time, they scale way too fast with the product of the population size, the total number of parameters, and the sequence length of your data.
And the fundamental operation itself is expensive.
It is. Calculating dollar plus ELIN and running the forward pass requires a separate full matrix multiplication for every single member, which just, well, it devours your resources.
So we end up with this paradox. Yeah. ES is theoretically parallelizable to millions of workers, but it's practically bottlenecked by the memory needed to generate the parameter sets for those workers in the first place.
That is the precise problem statement that EGGROLL answers. Its entire mission is to mitigate both of those bottlenecks, the memory and the computational ones simultaneously, to finally let us efficiently train billion-parameter neural networks using evolution strategies at hyperscale.
And here's where it gets really interesting. Because EGGROLL's solution is this brilliant mathematical shortcut. It's all about achieving that same high-quality optimization signal, but without paying the paralyzing cost of generating those full-rank matrices.
Yeah.
What is the core innovation that makes this possible?
The core idea is to substitute that full-rank perturbation, a dollar in brown dollars, with a low-rank approximation. So instead of sampling one massive matrix, EGGROLL samples two much smaller random matrices. We can call them ep-dollar. The dollar has dimensions, empt on downs earth, and the crucial difference here is that the rank, $10, is tiny. It's often chosen to be just 1 or 4. It's minuscule compared to the actual dimensions, art or dollars.
So we're replacing a full-rank matrix dollar with the outer product of two really skinny matrices. Frye appliance, the for dollar. This is the low-rank shortcut in action.
That's it.
For a listener who doesn't deal with matrix algebra every day, can you give us a quick analogy for what rank really means in this context?
Absolutely. Think of the rank of a matrix as the number of independent change vectors it can encode. A full rank matrix, dollars, can encode independent changes for every single one of its nollar times longer parameters. It has total freedom.
Right.
A low rank matrix, say rank 4% dollars, can only encode changes that are combinations of just those 4 primary vectors. You are drastically constraining the degrees of freedom of the change itself.
And this whole concept feels kind of familiar to anyone who's been following fine-tuning research. It really mirrors lower rank adaptation, which is used in gradient-based methods, but here it's being applied to the search space.
It's the exact same underlying mathematical principle, yes. Lower applies a low-rank adapter to the weights during fine-tuning. EGGROLL applies the same principle, but to the search perturbations that are used by the ES population.
And the genius is realizing it's enough.
The genius lies in realizing that for an ES search, a low-rank perturbation is actually sufficient as long as you average it across a large population.
Let's put some real numbers to this to truly appreciate the efficiency gain. If we have a matrix that's, say, 10,000 by 5,000, so that's 50 million parameters, what is the change in memory storage required for the perturbation for just one layer if we use, say, a rank of 2 average $1?
The memory savings are staggering. So for the full rank matrix, you'd need 1 part 8 times then, or $50 million units of storage. For the low rank matrices, 50 and $, the storage requirement drops to 1 men plus n low.
Okay.
So with O and $105,000 and poo in dollars, that's $10 times 15,000, which comes out to 150,000 units of storage.
Wait, hold on. From 50 million down to 150,000, that's nearly a 330-fold reduction in auxiliary storage. And that's per layer, per worker.
Precisely. And the computational savings follow the exact same pattern during the forward pass. The cost of running the forward pass for that perturbed layer drops from big O of money dollars to big O of 2 dollars plus NO. This mathematical streamlining just immediately slashes the compute burden.
But the efficiency gains don't just stop at the math. The paper highlights a really critical implementation detail about memory management. Because even if we're running thousands of workers, we still have to manage all these perturbations.
That's the other half of the implementation genius. Even though ONI dollars are small, if you have 10,000 workers, you still have 10,000 copies of ONI dollars. So to minimize data movement, EGGROLL uses a counter-based deterministic random number generator, an RNG.
So you're not actually storing the matrices.
You're not. Instead of storing the matrices NL dollars themselves, the system only needs to store the seed and the counter for each worker. The full perturbation dollars is reconstructed on demand during the forward path calculation rather than being persistent in memory.
That's clever.
It is, because memory bandwidth is so often the primary bottleneck on modern GPUs. This approach fundamentally reduces the amount of massive tensor movement required across the hardware, and that provides a further speed up right on top of the mathematical savings.
And this combination, the mathematical streamlining plus the intelligent memory reconstruction, that leads directly to the core scalability breakthrough. We talked about how traditional ES just crawls along. What is the normalized speed result that EGGROLL achieves?
The results are, well, they're revolutionary. EGGROLL achieves a 100-fold increase in training throughput for models with billions of parameters compared to standard ES methods like OpenES.
100-fold.
100-fold. To put that in context, if we normalize the speed of pure batch inference to 100, EGGROLL hits 91. It is running its fitness evaluations at near the theoretical maximum speed.
And meanwhile, the prior ES state-of-the-art OpenES is crawling along at what, 0.41?
0.41, and even established gradient methods like PPO, which rely on complex policy optimization, they only hit 34.
So you're telling us that EGGROLL has effectively brought evolution strategies up to the speed of inference?
That is the technical leap. It's unlocking near inference speed ES optimization for models of any size.
But I have to play devil's advocate here. I mean, if we are using rank 1 or maybe rank 4 perturbations for these massive matrices, that sounds like a tiny crack in a gigantic dam. Intuitively, it just feels like we must be limiting the search space. When does EGGROLL's low-rank approximation start to actively hurt the optimization performance?
That is the crucial, critical question. And if we were just using these low-rank matrices for a single isolated parameter update, your concern would be completely valid. The search space would absolutely be restricted. But you have to remember the nature of ES. It's population-based.
Right.
So while the individual perturbation, the EI for one worker, is low-rank dollars, the overall parameter update is calculated by averaging the contributions of the entire large population of non-dollar workers.
So the resulting total parameter update has a rank of minimum of non-dollars or teller.
You got it.
So even though each worker is contributing only this tiny ranked or dollar change, if you have a massive population silver, those small, independent, randomly chosen changes average out to cover the entire space.
Precisely. In the experiments, they make sure that the total rank, the Norrell-Weldon, is chosen to be greater than the minimum of Norrell-11. So, for example, if mile is $10,000 and it was $5,000, the minimum is $5,000.
Okay.
If they use population 1 of $10,000 workers and set the rank $3 to just 1, the total ranked Norrell is $10,000. Since 10,000 is greater than 5,000, the parameter updates are effectively full rank.
That's the magic.
That's the magic. EGGROLL maintains the full capacity of the optimization search space despite the dramatic memory and computational savings it gets from the individual low-rank perturbations. This is the synthesis of efficiency and efficacy.
So the practical success, and that counterpoint we just discussed, that low rank is sufficient because of the population averaging, it's all rigorously backed up by their theoretical analysis.
Okay.
EGGROLL isn't just some clever hack. It's underpinned by deep mathematical reasoning about the approximation accuracy of this low rank structure.
It is, and the convergence analysis in the source material was one of the most surprising mathematical nuggets for me in this whole thing. The theoretical analysis proves that the low-rank EGGROLL update converges to the true full-rank Gaussian ES update at a surprisingly fast rate.
Yeah, that rate is overread.
That ORO decay rate is the real aha moment. Because if you were just relying on standard statistical approximations that come from the central limit theorem, which, broadly describes how the sum of many independent random variables converges, you would typically expect a much slower rate.
Something like ORO rate.
Exactly. And the difference between ORO and $1 is just immense when ORO is small.
Can you elaborate on the practical consequence of that acceleration? What does that really mean?
Well, the difference determines feasibility. If the error decayed at OR to cut your approximation error in half, you would need to quadruple your rank tool. But if the error decays at OR dollars, you only need to double your rank to dollars. For EGGROLL to achieve the high level of accuracy they demonstrated within Eulers of just 1 or 4, if the approximation relied on that standard square root of tree rate, they would need exponentially higher rank values.
Maybe hundreds or thousands.
Potentially, yeah. And that would immediately negate all the computational and memory savings they gained. The rapid OR convergence is what makes the entire approach scalable and functional.
So why does EGGROLL beat the standard statistical bounds? Why is the convergence rate controlled by $3 instead of the square root of $2?
It boils down to symmetry. It's about the elimination of the lowest order error term. So we have to introduce a concept here called cumulants.
Okay.
Cumulants are measures used in statistics to quantify the shape of a probability distribution. They relate to moments like mean and variance, but they're particularly good at describing how much a distribution deviates from a perfect normal curve from a Gaussian.
And the lowest odd order one matters most here.
It does. The lowest odd order cumulant is the third order cumulant, which is essentially the skewness, the measure of asymmetry in the distribution. In many statistical approximations, this third-order cumulant term is the dominant error term, and that's what leads to the O-on-checker convergence rate.
But EGGROLL's perturbation vectors, the un and the dollars, they are specifically derived from zero-mean symmetric distributions.
Exactly. And because the underlying distributions are perfectly symmetric around the mean of 0, all of the odd-order cumulants, including that critical third-order term, they are exactly 0. They just vanish mathematically.
Which means the error is no longer controlled by that term. It's controlled by the next available one, the fourth-order term.
Correct. And that higher-order control term is what yields the accelerated OR-now decay rate. It's really an elegant demonstration of how carefully chosen search distributions leveraging symmetry can provide these massive practical benefits in approximation speed.
The theoretical finding also aligns perfectly with their empirical testing. The paper has this conceptual plot that visualizes how the approximation quality changes as the rank increases. What does that plot tell us visually?
It gives us this fantastic visual proof of concept. Even when the rank $1, which is the absolute minimum rank possible, representing the absolute maximum memory savings, the low rank approximation is already decent. It captures the fundamental shape of the true Gaussian distribution.
And it gets better quickly.
Very quickly. By the time you get to $200, the function has nearly converged, and by $300, it is visually indistinguishable from the theoretical infinite rank Gaussian limit.
That's a powerful statement. If a Norrell provides a sufficient optimization signal, it means researchers can run models with billions of parameters while only paying the memory and compute cost of a single parameter per layer per worker. The theory doesn't just support the hypothesis. It validates why the most extreme memory savings are possible without sacrificing the quality of the search.
It completely justifies the fundamental choice to rely on low-rank updates. The efficiency isn't achieved at the expense of search capability. It's a win-win.
Okay, so shifting focus now, let's talk about the applications. For me, the most compelling application of EGGROLL is demonstrating its ability to train models that gradient-based methods just couldn't even touch. They created this thing called the Evolved Generative GRU, or the EGG model. This wasn't just some test bed. This was an architecture designed purely for efficiency, regardless of any gradient constraints.
This is where the freedom from backpropagation really shines. Because ES is gradient-free, the architects were allowed to prioritize hardware-friendly constraints to maximize inference efficiency without worrying at all about the disastrous effects these choices would have on gradient stability.
And the EGG model was built under 3 specific constraints that would typically send a conventional gradient optimizer into, well, an immediate crisis. Constraint number 1.
Yeah.
Pure integer training.
This is a huge optimization step for any high-throughput system. Floating-point arithmetic is necessary for backpropagation because you need that high precision to accurately compute those tiny little derivatives.
But it's expensive.
It's computationally expensive and it's energy intensive. The fastest tensor core operation available on modern accelerators like H100s is int8 matrix multiplication with int32 accumulation. The EGG model is designed to leverage this speed.
So everything is integer.
Everything. All the weights are int8, all the activations are in integer formats, and the model never casts to floating point even during training. For hardware-constrained environments, edge devices, specialized accelerators, or situations where energy consumption is paramount, this is the holy grail.
And gradient descent just can't handle it.
No, gradient descent simply cannot handle this kind of low precision without massive stability issues. In gradient training, running in pure int8 often leads to immediate instability, loss spikes, and non-recoverable training because the precision loss just destroys the signal of those tiny gradients.
But ES is fine with it.
ES, because it relies on the overall fitness score, is far more tolerant of noisy internal calculations.
Okay, so constraint number 2 was the use of a nonlinear RNN specifically, a variant of the MinGRU model. Why is that typically a problem for gradient training, and how does EGGROLL bypass it?
The problem is something called backpropagation through time, or BPTT. RNNs maintain a hidden state that carries information across sequence lengths. When you calculate a gradient, you have to propagate that error signal backwards, not just through the layers of the network, but backwards through time across all the time steps of the sequence.
And for long sequences, that's a nightmare.
It is. For long sequences, this BPTT mechanism quickly leads to exploding or vanishing gradients, which makes stable training impossible. It's why architectures like the transformer, which relies on attention and parallel computation rather than sequential state, became so dominant.
But ES doesn't need BPTT.
Not at all. Since ES relies only on the outcome reward at the very end of the sequence, it completely avoids BPTT, and that allows for stable training of these very efficient recurrent models on arbitrarily long sequences.
So we have int8, we have RNNs, and then the third constraint seems really counterintuitive for a network that needs to model complex functions. They removed all standard explicit activation functions like ReLU or TAN. If you remove the explicit nonlinearity, how does the model learn anything complex?
This is the subtle beauty of optimizing for the hardware constraints. The nonlinearity is provided implicitly by the hardware itself, specifically by the saturated addition of int8 values.
Ah, the clipping.
The clipping. Since int8 values have such a narrow dynamic range, any addition that exceeds 127 or drops below -128 results in saturation, which acts as a hard clipping function. The saturation is inherently a nonlinear operation.
And ES can find that.
EGGROLL, through its massive population-based search, is uniquely able to exploit and learn to maximize the effect of this implicit clipping nonlinearity that's buried deep within the low-precision arithmetic. They even went one step further, using a variant of L1 normalization instead of the standard L2 norm, specifically to avoid complex floating-point operations like square roots, maintaining that pure integer pipeline.
That is a remarkable demonstration of optimizing for the hardware first. So how did this gradient hostile efficiency maximized AG model actually perform on a character-level prediction task.
The results really confirmed the stability hypothesis. During pre-training on the Minipile dataset, the training was remarkably stable. They observed none of the loss spikes, the NANs, or the catastrophic instabilities that are the hallmarks of attempting backprop training at these low precisions.
And the scale.
The scale is what EGGROLL enabled. They managed to scale the population size up to an unprecedented 262,144 workers.
That number is just...
Yeah, it is. To put that into perspective, that is 2 full orders of magnitude larger than the largest populations we've seen in prior successful ES work. This vast population, made possible by that near-inference speed efficiency, allowed them to thoroughly sample the complex search space of the EGG model.
But was that sheer scale purely for, bragging rights, or was that massive population size fundamentally necessary for the optimization quality?
That leads to one of the most important ablation insights of the entire paper. They ran an experiment where they controlled for the amount of data processed. So both large and small populations saw the exact same amount of data. But the difference was the number of unique perturbations they encountered.
And what did they find?
They found that training with a tiny population size, specifically N22, which is sort of analogous to simple zeroth order optimization, was highly unstable, and it often failed completely. You need those unique perturbation directions.
So if you run the same amount of data through a tiny population, you fail. But if you run the same amount of data through a huge EGGROLL population, you succeed. What does that tell us about the nature of the optimization required for pre-training?
It tells us that for successful pre-training of complex architectures from scratch, maximizing the number of unique parameter changes you sample is absolutely essential. Zeroth order methods, which rely on minimal perturbations, are just insufficient for this kind of exploration.
So the big population is a requirement, not a luxury.
It's a necessary ingredient for pre-training stability and performance. That massive population size, enabled by EGGROLL's efficiency and low-rank approach, is what ensures that across the large search space of billions of parameters, the averaged update is truly full rank and robust.
So what does this all mean for real-world applications? We've seen the theoretical elegance, the computational speed-up, and the ability to train these impossible architectures. Now, let's look at the empirical success across 2 major domains: traditional reinforcement learning and the bleeding edge of large language model fine-tuning.
Let's start with RL, which is really ES's home turf. They benchmarked EGGROLL against OpenEase, which was the former standard, across a really diverse set of 16 environments from major suites like Navix, Craftax, Brax, Kinetics, and Jumanji.
And the goal is to test if the efficiency gains compromise the quality of the policy that was learned.
Exactly. And what was the verdict on performance quality?
What did they find?
EGGROLL performed exceptionally well. It outperformed OpenES in 7 out of the 16 environments. It underperformed in only 2, and it was competitive or basically equivalent in all the rest.
So the consistency is there.
The performance consistency is critical. It shows that EGGROLL's low-rank, high-speed approach is not a quality trade-off. It maintains state-of-the-art optimization quality while fundamentally changing the speed equation.
And that speed advantage is the utility that scales. Were there any domains that saw particularly dramatic wall clock time savings?
Absolutely. When the network sizes increased, OpenES often just became completely infeasible to run. But even where it was feasible, the speed differences were profound. In multi-agent RL settings, for instance, in scenarios like simple reference, EGGROLL trained up to 2.4 times faster than OpenES when using large batch sizes.
Okay, that's significant.
And we saw an even more drastic result in the Jumanji Snake environment, which requires really fast, iterative training. In that one, EGGROLL was over 40 times faster than OpenES.
40 times?
40. This isn't just a marginal improvement. This means what used to take weeks of cluster time now takes hours or maybe days. It dramatically accelerates the RL research cycle, allowing researchers to iterate on algorithms and policies far more quickly.
Okay, now moving to LLM fine-tuning. This is a domain where those outcome-only rewards are very common, making it a perfect fit for ES. They use the RWK-V7 recurrent models as a test platform, right?
That's right. They chose them because their constant state size makes them particularly suitable for massive parallelization, which perfectly leverages EGGROLL's speed. They benchmarked against GRPO gradient reinforced policy optimization.
And GRPO is a key baseline here because it's one of the leading methods for using gradient techniques to handle these non-differentiable rewards in LLM fine-tuning. It often relies on policy gradient methods to approximate the signal.
Right, it's the gradient-based contender.
So let's look at the numbers for reasoning tasks. They started with the countdown task on a smaller 1.5 billion parameter model.
On Countdown, which is a numerical reasoning benchmark, EGGROLL fine-tuning converged to 35% validation accuracy. This was a significant lead over GRPO, which only managed 23% accuracy, and this was achieved under identical hardware and wall clock time constraints.
So it shows superior optimization efficiency.
Exactly, when running at scale.
And how did this success then scale to larger models and more complex reasoning benchmarks like GSM-8K?
On the 7 billion parameter model for the GSM-8K math reasoning task running on 8 GPUs, EGGROLL again consistently outperformed the GRPO baseline. But the real performance peak came when they scaled up the RWKV-7G7B model again on that countdown task. Here, EGGROLL reached an impressive 72.9% validation accuracy.
That 72.9% number needs some serious context, especially when you compare it to other published results in the literature. What does that percentage victory actually signify?
It signifies that the optimization method itself is the source of the superior performance, not just the underlying model architecture. That 72.9% accuracy outperformed the reported results of OpenES, which was 66.8%, and GRPO, which was 52.8%, published by other research groups.
And this is the key part.
This is the key part. Even though those competitor results were achieved using a potentially stronger, highly established base model, the Qwen 2.57B model.
Wow, so that's a huge win. It means that EGGROLL's ability to leverage these massive population sizes, which is its unique scaling advantage, is crucial for extracting maximum performance from LLMs on these complex, reasoning-heavy, outcome-only tasks.
It shows that scaling the optimization method is just as important as scaling the model size.
Now, since this fine-tuning relies entirely on non-differentiable rewards, they had to be incredibly careful about how they constructed the fitness signal to avoid noise. Can you give us a bit more detail on the sophisticated scoring mechanism they used for the LLMs?
Certainly. They didn't just rely on raw accuracy. They used two key techniques to shape a really clean fitness signal. First, they employed an antithetical pair-based fitness shaping scheme. This is pretty standard in ES.
Okay.
For every perturbed parameter set, so W plus ELI, they also evaluate the exact opposite perturbation, W equal to I. This helps to reduce the variance of the fitness estimates.
And the second technique?
Second, the final scoring function was really carefully crafted. It computed a z-score per question. So they didn't just average raw results. They standardized the performance of the worker relative to the mean and standard deviation of all questions in that specific batch. This z-score was then averaged over all the questions to compute the final score. This whole process drastically cleans up the noisy, sparse reward signal, and it ensures that every worker receives a consistent, high-quality optimization signal despite the complex, outcome-only reward structure of the reasoning task.
So it really sounds like the entire EGGROLL system is this masterclass in synthesis, maximizing hardware efficiency within J8, maximizing search efficiency with low-rank perturbations, and then maximizing signal quality with this antithetical z-score shaping.
That's precisely right. It's a completely cohesive approach that unlocks true hyperscale ES.
So to summarize what we've unpacked in this incredibly deep dive, EGGROLL successfully scales evolution strategies to the multi-billion parameter regime. It fundamentally solves the computational bottlenecks that prevented ES from reaching its full potential for so long.
And it achieves this by using those low-rank search matrices, which provide immense computational and memory savings, even down to a rank of $1 with negligible performance decrease, all because the population-based update remains effectively full rank.
And the practical outcome is huge. 100-fold speedup over Naïve ES, making it practical for real-world scenarios and the opening up of entirely new architectural design choices.
Right, like the pure integer language models that were previously just impossible to train with standard gradient descent because of the inherent instability.
That fundamental advantage, the liberation from the calculus constraint, that feels like the engine that's going to drive the future potential of this work. If a system component is non-differentiable, EGGROLL is now a viable, scalable option for optimization.
It is.
So that raises the question of where this all goes next. Considering EGGROLL's strength in handling these non-differentiable systems, what are the most exciting applications that researchers are eyeing for the future?
The research really points toward two deeply fascinating areas that are currently major challenges for the AI community. First is the training of large-scale neurosymbolic systems.
So these are systems where neural networks are interfacing directly with classic symbolic modules, things like complex external databases, sophisticated logic engines, or just precise calculators.
Exactly. And these symbolic modules, they perform non-differentiable operations. If a neural network wants to consult an external memory bank, that lookup function is often discrete and non-differentiable. Training these integrated end-to-end systems has been incredibly messy.
Yeah, it requires complex gradient approximations or workarounds like RLHF.
Right. And EGGROLL can train the neural component and the integration logic together purely based on the outcome of the overall system.
And what about the second area?
It's optimizing complex end-to-end systems of language models, especially those involved in multi-agent collaboration. Imagine training a system of different LLM agents where the reward is based purely on the success of their final collective task or their strategic interaction in some complex environment.
That sounds incredibly difficult to optimize.
It is. The complexity of their communication protocols, their use of external inference time harnesses, and their interaction dynamics make standard gradient calculations virtually impossible to define or stabilize. EGGROLL just treats the entire multi-agent system as a single black box.
It just looks at the results.
It just looks at the resulting fitness score, the success or failure of the collective, and it optimizes the billions of parameters within those agents based on that outcome. It makes it ideal for large-scale, goal-oriented, multi-agent AI.
That really does redefine system design. I mean, we've spent a decade optimizing our models to be backpropagation compatible, even if it meant sacrificing efficiency or utility. Now we have a tool that lets engineers design components that prioritize ultimate efficiency and functionality, knowing that a scalable optimizer actually exists.
It's the moment where optimization finally catches up to architectural ambition.
That raises a final provocative thought for you to explore as you step away from this deep dive. Considering that current AI systems often struggle with interacting robustly with external tools or memory modules without all these complex gradient workarounds, how might EGGROLL fundamentally change the way we design and train truly integrated, robust AI systems in the future? Does this mark the beginning of the end for the tyranny of the gradient in deep learning?
It's certainly a paradigm shift. It liberates design from the constraints of calculus, and it allows engineers to finally ask, what is the most efficient system, rather than just what is the most differentiable one?
An incredible deep dive into EGGROLL. Thank you so much for guiding us through the mechanics and the monumental implications of this work.
It's always a pleasure.
And thank you for joining us on the deep dive. We'll be back soon with more essential knowledge.